there's some questions like this on the 1.3 assignment. You're going to get some more at the end of the chapter when we do our kind of our review, our study guide before the test. This is a big deal. Something we do a lot in geometry, a lot in math. We got to be able to find distances. Okay, so let's quickly review this. Remember, I don't want you, I hate to use the word distance formula. We don't want to rely on formulas. We want to rely on kind of conceptual relationships, right? We want to find a distance, though. What was our trick? How did we think about a distance? If I've got 2 points, let's say point A and point B, and we graphed them, what's our trick for finding a distance there? It doesn't mean we have to remember a big long formula. Yeah, the triangle, good. We're going to draw a right triangle, and we're going to use the Pythagorean theorem, right? So the distance between A and B, we'll just call that D, and it's just going to be the hypotenuse of a right triangle, right? So if we make a right triangle with a horizontal leg and a vertical leg, now think about this in terms of an ant crawling from point A to point B. If we want to know what's the shortest distance the ant could crawl, well, that's D, right? That's the hypotenuse. But if the ant crawls in 2 steps, if he crawls horizontally and then vertically, right? What do we call the horizontal part of the ant's journey? Keeping in mind that in the XY plane, the x-axis is the horizontal axis and the y-axis is the vertical axis, right? So what do we call this? Say, what is it again? Delta x, good. Delta means change in, so it's going to be the change in the x-coordinates of the 2 points. What do we call the vertical part of the journey, the vertical leg? Delta y.
That's supposed to be a D or a triangle?
It's supposed to be a triangle. Yeah, delta, this is delta. Delta is it's a capital D in Greek, is what that really is. So that's how we write it. Okay, so then what does the Pythagorean theorem tell us about this triangle? Let me have everybody put your phones away, please. Phones got to be put away. I don't want any distractions. Okay, so what's the Pythagorean theorem tell us about this? What's Pythagorean theorem say? If we have a right triangle where the legs are A and B and the hypotenuse is always C, what's it tell us? A squared plus B squared equals C squared. Good. Well, we don't have A's and B's and C's here, but it's still a right triangle. So what's the Pythagorean relationship here? What do you think? Okay, good. So delta x squared, that's one of the legs, the horizontal leg, plus delta y squared equals d squared, where d is the hypotenuse, that's the distance, that's what we want, right? Simple. It's just a Pythagorean relationship. It's a right triangle, right? What do we do, though, in this case, if we want to, we don't really want d squared. We want to know what is d. So how do we undo squaring something in math? Square root it. So if we square root both sides of the equation, it's an equation, so both sides have to be treated equally. We end up with d on the left. We undid the squaring, that's good. On the right, then, we've got a big square root. The square root of that stuff, right? Delta x squared plus delta y squared. And that's our new, improved, simpler distance formula. It's just the Pythagorean theorem. Okay, so let's do this problem, though, now. Really, all we've ever got to do when we're trying to find a distance is we've just got to find out what delta x and delta y are. And real quick, let me draw your attention to the specific instructions here. What do they want us to give in terms of an answer? What should it look like? It's a decimal. In this case, it's rounded to the nearest tenth. So this is just going to be a decimal. These are the easy ones because we don't have to do any kind of simplifying the radical, right? We're just going to put it in a calculator and get an answer. So what is delta x in this case? Now, don't give me a direct answer, but I want to know if I'm finding delta x, I've got to find the difference in the x values. Remember, we always want to find the biggest x value and subtract the smallest x value. Kylie, what are the 2 x values of our points in this problem? Negative 10 and 8. Which one's bigger? And bigger is a bad word. What I really should say is greater, right? You're right. 8 is greater, isn't it? And by greater, we mean if we look at it on a number line, So here's 8. Then wouldn't, if that's 0, wouldn't negative 10 be clear down there somewhere? Right? Okay, so 8 is greater. We all have that idea. So 8 is greater than negative 10. Okay, so then delta x is going to be the greater one minus the lesser one. But remember how we do that. If we subtract a negative, what are we really doing? Adding. And the way you can think of it is this way. Minus a negative just makes a plus sign, right? Minus a negative. So we get 8 plus 10 is what? 18. Delta x is 18. Good. Okay, what about the y's? Shaw, what are the two y coordinates in those points?
9 and 5.
9 and 5. Which is bigger?
9.
9. So delta y is then going to be what minus what?
9 minus 5.
9 minus 5. Good. Which is 4, right? So now all we have to do is just take those two values and plug them into the Pythagorean theorem. That's it. So we end up with d equals the square root of 18, that's my delta x, squared, plus delta y is 4 squared. Remember, we want to get positive values because if we don't, we've got the danger of mis-squaring them in the calculator. You have to put negative numbers in parentheses. That's a pain. It's easy to forget. But if you always follow this scheme for finding delta x and delta y, subtract the smaller from the bigger, you're always going to get positive answers, which makes sense because we're thinking about this in terms of a triangle, and the lengths of the sides of a triangle are always positive, right? It really does make it easier to do this without making mistakes if you do it this way. So then the last step is really just a calculator step. All we're going to do is just put this stuff into our calculator and get an answer as a decimal. We could simplify this number in here. When I say simplify, we could square out 18 and square out 4 and add them up. That's fine. But you don't even have to. And this is one of the really main reasons that I highly recommend people use a graphing calculator, because it's just so much easier. Sure, you can do lots of big high power stuff that you'll do in a little bit in here, but more in future years. But also it's a way easier way to just make computations without making mistakes. Things look like they're supposed to on the screen. So if I want to get this number on the graphing calculator, all I do is just pull up the square root, put in an 18 squared plus 4 squared, and look, it looks just like it's supposed to, right? It looks just on the screen, it looks just like that. So when I hit enter, it gives me back a decimal. We're supposed to round to the nearest tenth, so 1 decimal place. So what are we going to get? 18.4, yeah. So this answer, and that's the squiggly equal signs mean approximately, right? So we're going to give a decimal answer. So it's approximately 18.4. That's what I'd put into Moodle, and I'd have it right. Okay, questions? Okay, let's look at one more of those. Slightly different. Okay, what's different about the instructions here? Exact. Yeah, we want an exact answer representing this distance, right? So let's calculate our delta x and delta y. So what about delta x? Molly, what are the two x values of those points? 4 and 10. Which is bigger? 10. So we just get 10 minus 4 equals 6, right? Okay, let's see. Madison, what are the two y values? 7 and 1. So we get bigger minus smaller also equals 6. And so if we take those values and we just put them into our Pythagorean formula, so distance equals the square root of delta x squared plus delta y squared, we get the square root of 6 squared plus 6 squared. Now this time, we can't just pop them in a calculator though, because we want an exact answer. So we do need to simplify this. So what's 6 squared? 36 plus 36. What's 36 plus 36? 72. Okay. So now we got to go back and you can see why we practiced this so much at the beginning of the year. So we got to find a perfect square that divides into 72. Well, what's a pretty obvious one here? 36. Yeah, 36 times 2, right? 36 plus 36 is the same thing as 36 times 2, right? So we can rewrite this as the square root of 36 times the square root of 2. And what's the square root of 36? 6. So there's our answer. That's what we have to put in the middle. Okay, let's do that. Let's verify that it works. So I got to pull up my editor. Of course, it's on the other screen. Okay, so grab, oops, I didn't mean to do that. There we go. So it was, what was it, 6 radical 2? So 6 square root 2. Okay, looks good. Check it. We got it. Okay, makes sense? All right. Okay, so today I want to just look at a couple new things. Okay, here we go. All right, so angles and their measures. All right, so let's quickly just kind of a review of angles. A lot of this stuff you're going to have seen, but maybe some of it you haven't. So first, let's talk about just how we treat angles. So we got a symbol for angle, right? It's just it looks like an angle. Sometimes in Moodle we'll use a less than sign, because a lot of time, or in any technology, when you're in college and you're doing this stuff on computers there also, a lot of times you'll just use the less than sign because it kind of looks like an angle. So what are angles? Angles are just made, they're really simple. They're just two rays that share a common initial point. So they look like this. There's two rays. Name one of the rays for me. Brady, what's one of those two rays? How would you say it? Ray XY. Good. So we got ray XY. What's the other ray? Ray XZ. They both start at X. One of them goes through Y. One of them goes through Z. Notice they have a common initial point X. Okay. So we call the two rays, we call the sides of the angle. So they sort of enclose the angle. And the common initial point we call the vertex. Okay, so that's sort of the anatomy of an angle. That's it. Two sides and a vertex make an angle. So what do we name this thing? I'm going to hide that for a second. Can somebody tell me one good name for this angle? What's one thing we could name this? What do you think? Angle YXZ works. That's fine. So YXZ. Make a list over here. Angle YXZ. Can somebody tell me another name for this angle? What do you think? Say it again. ZXY works. Another one. Okay, it is. That's the kind of angle it is. It's cute. If I want to specifically, label that angle, that specific one. What else? Is there any other way? Can you think of to name that thing? Let me ask you this. Could I name it angle XYZ? Does that work? I'm hearing some no's. How come? Okay, yeah, there has to be a specific order here. When you name an angle with 3 points, and that's a great way to do it. That's probably the best, most accurate, precise way of naming an angle. It's like you're giving an ant a roadmap to walk that angle. So you're telling them either start at Y, for example, if we use this one, travel through X, and then go through Z, right? That names the angle. That works. Or I could tell the ant to start at Z go through X, and then go to Y. So notice that the vertex has to be the middle destination in that trip, right? It has to be the middle value. If I ask the ant to do this, if I asked him to start at X, go to Y, and then go to Z, that's the wrong angle, right? That doesn't work. So that one's no good. What else could we name it, though? Any other suggestions? Being as there's only one angle represented here, we could actually also call this angle X. That works. That's a little tricky, though. You gotta be careful with that, and we'll see why in a second. So there are some possibilities: angle YXZ, angle ZXY, or angle X. Or we could even do something like this. If I put like a number in there, for example, that means that 5 represents that angle. So we could also call it angle 5. That also works. Okay, what about this one though? Let's say we're referring to, how about this top angle up here? Can I call that one angle B?
No.
Why can't I call that angle B, do you think? What's wrong with that? Lacey, what's wrong with that? Why can't I call that, here's the one I want to name right up here. What's wrong with calling that angle B?
Because it's not just, it's A, B.
Okay, yeah, and if I call it B,
It's just.
that's not very clear, is it? Right? Angle B could mean angle ABD, but what else could it maybe mean here? Yeah, it could mean a different one. It could mean like ABC, or it could mean DBC or something, right? So when I have multiple angles that share the same vertex, then I can't use this shortcut. It's not specific enough, right? So in this case, that doesn't work. Okay, angle measurement. All right, angle measurement. We had, just to kind of make this point, I want to throw in just a tiny bit of review here. Remember, this may not seem like a big deal, but this really does help. Remember earlier in the year, we talked about how we can break up, we looked at the example with we put like the soup cans on the slide, and remember that thing we talked about, we rolled them down? And we said that there was a difference there because one of them was on a really slippery surface, and so it could slide. The other one was on a rougher surface, so it had to roll, and the motion was different, right? That's a big deal. In physics, where we study the way things work, we study motion and we study forces and things like that, we have to be very careful about that because we know that rotational motion is a real thing. It takes energy to make something rotate, just like it takes energy to make something go from point A to point B. And so mathematically, we need a way to discuss that. And we said that we can't. We've got 2 different ways of thinking about things. We can think about kind of straight line types of things, which we've already talked about last section. We talked about segments and rays and lines, and let's just take a segment, for example. If I'm taking a segment that goes from A to B, we could talk about a length of that segment, couldn't we, right? And that means something to us. It means how far apart are those points. When we want to talk about angles, we have to be able to do the same kind of thing. We have to be able to say in an angular sense, which is a little harder to wrap your brain around. We have to be able to say how far apart are, for example, this is point A, and that's point B, and that's point C. Sure, we might want to talk about the length of that segment. So how far apart are they linearly, meaning how far apart in terms of a distance? Sure. But we might also want to know how far apart are they angularly. Let's say, for example, that this is the fulcrum, or this is like the center of a wheel or something, and point A is really just a dot of paint on the wheel of a bike or something. As the wheel rotates, would you agree that that point A is going to do something like that? That makes sense? We might want to know, well, how far apart are points A and C in terms of the angle, right? How big an angle does that tire have to rotate through for point A to line up with point C, right? That's legitimate too, right? That's a kind of distance, only it's an angular distance. So we call that an angle, and we measure it typically in degrees. You know, later on when you get into higher level math classes, a lot of times we'll trade degrees for something called radians. We won't really do that so much this year, but there's just another way of measuring angles. For now, we'll just stick with degrees though. Okay, so what about this then? how do we say it? Well, first of all, we would measure angles with maybe a protractor. Just like we'd measure distances with a ruler, we'd measure angles with a protractor. We won't really do that. We'll use some technology in the lab to measure angles. Units would be degrees, but this is kind of important. If we had, for example, point A and point B, how did I say that thing right there? What is it that I just drew? What is that blue thing that I drew that extends from point A to point B? It's a segment. Good. It's a segment AB. How do I write that in geometry? How would I write that? What's the symbol for a segment? Okay, so it's AB with a segment symbol over the top, right? Does that make sense? Could I call that, by the way, could I call that segment BA? I could. It'd be fine, wouldn't it? The order doesn't really make any difference there, does it? Okay, so that means one thing, but what if I want to talk about the length of that segment? That's not a geometric thing, that's a number. How do I write that? Let's just say, for example, that we know that it's 10. How would I write that statement in geometry, that the length of segment AB is 10? Remember? We haven't done a lot of this yet. We'll do more. Say it again. What equals 10 though? Yeah, something equals 10. What equals 10? What goes there? Ah, okay, yeah, there's no symbol, it's just an A, B. Remember what that means. If there's no symbol over the top, then it's not a geometric thing, it's a measure, it's a number, right? So what we're saying is, we could think of it two ways. Either it's the length of segment AB, or I could even just think about it as a distance, right? The distance from A to B. Make sense? Okay, so that's different from that. That's a geometric thing, that's a number. Same thing is true with angles. If I've got angle A, that's something I can draw, that's a geometric thing. But if I want to know how big that angle is, I write it as the measure of angle A. Maybe it's 40 degrees, for example. Okay, make sense? Okay, there's something that goes with this. It's not complicated, but I want you to be aware of this, because this is a place where people make simple mistakes. In geometry, there's a couple important words. Have we talked about congruent yet? We mentioned that word even. It's sort of like equal. So if we talk about congruence, so something is congruent to something else. There's two parts to being congruent. Objects that are congruent have two things that are equal. Do you know what they are? Same shape and same size. Okay, congruence has to have same shape and same size. Okay, so for example, if I drew a triangle, which we'll do later, there's a triangle, and I copy this triangle, and I can even do something like rotate it a little bit. But those two triangles are the same shape and the same size, aren't they? You just saw me copy them. So I would say that those two triangles are congruent, right? It's not correct to say that they're equal, because they're not numbers. They're things. There's a big difference. We say that objects are congruent, but numbers are equal, okay? So that would be an incorrect, if this one is triangle, let's just call this one triangle A, and let's call this one triangle B. This is not a correct statement. That's just a symbol for triangle also. So triangle A is not equal to triangle B. Doesn't work, because they're not numbers, they're things. What we have to do instead is we have to say that they're congruent, and that's our symbol for it. Okay? It's like an equal sign with a squiggly. It's called a tilde, but it doesn't matter. It's an equal sign with a squiggly on top. That is reserved for geometric things. Okay? So with segments, they're pretty simple. They're pretty basic. If I've got segment AB, which has a length of 10, and I have segment CD, which also has a length of 10, somebody tell me a relationship that I can write about those two segments. What's one thing I could say? Okay, I could. Yeah, I could say that the length of segment AB is what? How is it related to the length of segment CD? Equal. They're equal because they're numbers. Does that make sense? That's a true statement. The length of AB, which is 10, is equal to the length of segment CD, which is also 10. Okay, can you say something else about those? Serena, can you tell me some other relationship I can say that doesn't use an equal sign instead? I'll start you off. Segment AB, okay, is equal to segment CD. Do we agree? Somebody want to slightly tweak that? Congruent. Yeah, that's not true, but this is. Because now they're segments, they're things, they're not measures. Does that make sense? So because they're things I can draw, I have to say that they're congruent, same shape and same size. Segments are all the same shape, they're just straight, right? But the size part has to do with the length of the segment. Agreed? So that also has to be true. Okay? With angles, same deal. One other thing I need to add here. How do we represent that in terms of a picture? Simple. All we do in geometry is we put a little dash mark through them, just a little hash. And that tells me that those two segments are congruent. Okay, now what if I have something like this though? What if I have a situation where I've got, let's say another segment here, BE, that has a length of 6, and there's another segment over here, DF, that also has a length of 6. Okay, those are congruent to themselves, aren't they? But this would be incorrect for me to do that, wouldn't it? Yeah, so I got to put 2 of them because that would be saying that all 4 of those are congruent. Now I'd have to do something like that. I'll put 2 hashes with segments B, E, and DF to show that they're congruent to each other, but not congruent to the others. Does that make sense? Okay. What about with angles? Same kind of deal with angles. If I've got angle say we measure these angles, and the measure of angle, I think I need one more. So the measure of angle BAC is 20, the measure of angle DAB is 30 degrees, I should say. EAD is 20 degrees. FAE is 30 degrees. So I want a Caitlin, give me a statement I can make about those that's true. I'll get you started. So you just fill in the blank. So what if I said the measure of angle BAC, finish that. Equals, good, because it's a measure, it has to be equals. Yeah, equals the measure of angle EAD. True, because those are numbers that are equal to each other, right? Okay, Justine, give me another statement up here that's true that doesn't use an equal sign. I'll start you off. You just finish it. What if I say angle BAD? Okay, so what's the other angle you're going to compare it to? Angle ACB. Okay, so let's look at. Let me just draw something up that might help a little bit. So here's the angle we're talking about. Angle BAD is this one, isn't it? Right. So it's that angle right there. So AD. Say it again. I'm sorry, I missed that. ADE. Okay, so well we have to say maybe DAE. That one's 20 and this one's 30. The measures. So what's another one? Alec, you got an idea?
AFE.
Okay, but how would you? But what's the angle order they have to go in? Because if you did AFE, you're telling me this angle. You're telling me AFE. So what's it going to be? Okay, good. So angle FAE would be congruent to that one, wouldn't it? Right? Now, those are angles. Those are angles, so I can't say them equal. They're things I draw, right? So I'd say angle BAD is what to angle FAE? Good. Congruent. Yeah. Does that make sense? Okay. All right. How do you suppose I would say with symbols? How do you suppose I would show that angles EAD and DAC are congruent with symbols? Now this is, by the way, I didn't maybe say this, but this is our technique for showing congruence of angles. We just put a little loop in there, right? Ah, two of them. Yeah, so I could do this. I could say that one and that one are congruent. Does that make sense? Okay, that's another way that sometimes books do it, but we're not going to do that. We're just going to use the number of loops. Okay? Okay? Good question, though. All right. Okay, so real quick, back to it here. Hang on. So angles with the same measures are congruent. All angles look the same, but if they have the same measures, it also makes them the same size. So they're congruent. Okay? So if the measure of angle A equals the measure of angle B, then angle A is congruent to angle B. Protractor postulate, I'll just throw this at you, but it's not a big deal. This is kind of it's really just common sense stuff. Remember, previously we had the ruler postulate, which just said that if we have 2 points, we can measure a distance between those points. That's it, right? We can't, with using some units, we could measure a distance. All this says is if we have an angle, we could measure the size of that angle with degrees, for example, using a protractor. Okay? No big deal. Okay, interior or exterior. If I've got an angle here, name a point that you think might be on the interior of that angle. B, because it's inside the angle. Good. So B is on the interior. What do you think we would label the area where C is? Exterior, because it's outside. Okay. And D is on the angle, right? Okay, angle addition postulate. This is an easy one too if you just think about it in terms of what we did earlier. Remember, if we had something like this, if we had point A and point C, and somewhere in between A and C was point B, what can we say about the lengths of those segments? How can we relate the length of segment AB, the length of segment BC, and the length of segment AC? Martin, what do you think? How can I relate those three things? What has to be true? So I want you to, here are the three quantities that we're relating. The length of segment AB, the length of segment AC, and the length of segment BC. Could I set up an equation there? Somebody help me out here. What do you think? Okay, that makes sense, doesn't it? Because, like, for example, if AB had a length of 5 and BC had a length of 7, Martin, what would the length of the whole thing have to be? Oh, 12, the sum of the two, right? It'd be 12. Yeah, it'd be 5 plus 7, right? So that makes sense then. We can say, this is the segment addition postulate. If B is a point that's between A and C, then the length of segment AB plus the length of segment BC has to equal the length of segment AC, right? And you're currently doing some stuff with that on this 1.3 assignment. The angle addition postulate is just the angular equivalent of that relationship. It's the same thing. If P is some point that's in the interior of angle, well, they did that wrong, didn't they? That angle's not RST, is it? That's wrong. What should that angle be? Yeah, it should be like QRS. What in the world was that? I don't know. Angle QRS. Then this is true, right? Then could we say this? Angle QRP plus measure of angle PRS would have to equal the whole thing. Make sense? We're almost out of here, aren't we? Yep. Okay. That's probably good for today. There's one last little thing I want to do, but we'll handle it tomorrow and go to the lab.
Because I gave you